So what I'm assuming today that we've all seen vectors before. So a lot of the stuff we're going to go over fairly quickly. So we're in section 11.1, our last chapter this semester.
Really? How long?
It is. We'll have 2 quizzes this chapter. But yeah, this will take us to the end. But we have a week vacation in the middle.
Yeah.
So.
All right. I'm down.
All right. So just to make a distinction, just to remind ourselves about the distinction. Let's get started, guys. If we have a magnitude with, or a quantity with magnitude only, that is a scalar. We're talking about quantities that have magnitude and direction. And those are vectors. And we're going to be talking about vectors. So the basic idea of a vector, just to kind of go back to the very beginning, a vector is directed, we think of it as a directed line segment. And just a little bit of terminology quickly. So if this is our vector, and we call that point A, and the terminal point here B, we call A the initial point, and B is the terminal point. Just so we have our terminology down. And any directed segment with the same magnitude and direction is equivalent. So they don't have to, as long as it has the same magnitude and direction, we consider those vectors equivalent. We usually, in writing, in the textbook, vectors are usually printed in bold. And we usually use lowercase letters, usually. In handwriting, what I'll do, the way I'll note vectors is with the little arrow over the top. So we'll talk about vector U or vector V. So with the little arrow over the top. If our initial point is at the origin, then our vectors, we call it the vectors in standard position, if our initial point is at the origin. And so if our initial point is 0, 0, and our terminal point is V1, V2, then we write V, our vector V, equals, and we use these braces, V1, V2. So these angled brackets denote a vector. And I'll try to use all the various different notations. We'll kind of use them interchangeably. We'll use the hat notation. We'll use this bracket notation as well. This is called the component form. So we're just listing in brackets the components of our vector. And it's also important to note that the 0 vector is 0, 0. And the 0 vector, this is a mistake that people make every year, the 0 vector does not equal the 0 scalar. They are different things. So a 0 vector is the vector with no magnitude. And the 0 scalar is a scalar with no magnitude. One is a vector, one is a scalar. So they're different things. Now, are we all familiar with how we add, subtract vectors? When we add vectors, we add their components. When we subtract their components. We multiply by a scalar. We multiply each scalar by a component, or each component by the scalar. And adding, if we're thinking about adding geometrically, we're putting the vectors head to tail. If we're thinking of subtracting geometrically, we take the negative one vector and put them head to tail. Everybody familiar with those things? Okay.
Sound vaguely familiar?
What's that?
It sounds vaguely familiar.
So, I guess if we feel fairly confident with that, I'm not going to list out all the properties, list out how we add vectors, how we subtract vectors. I think that's something that we've all seen before. And I'm not going to list all the properties of vectors. Commutative property, associative property, all those properties. Vectors have essentially all the same properties as scalars. And when we talk about dot product and cross products, we're talking about addition and subtraction today. Dot product and cross product are how we multiply vectors, and we'll talk about that separately. All right, we'll talk about the length of a vector quickly. Length of a vector. If we have a vector v, we write v, the length, like so, and our length is just the square root of the components squared.
Is that also the same as magnitude?
The magnitude, the length, magnitude, the same thing. So we can say length or magnitude. We call V the norm. Of our vector if the length is 1 or if the magnitude is 1. So what we're so V would be a unit vector in this case. So a unit vector just means a vector with length or magnitude 1. And if our vector is a vector between 2 points, how would we represent the length or the magnitude in that case? Square root of, we'll do it in this order, Q1 minus P1 squared plus Q2 minus P2 squared. So we're just using the Pythagorean theorem here. So this is how we find the length of a vector. If we want to find a unit vector in the direction of v, that's going to be something that's important that we'll use very often, especially second semester. So we want a unit vector is v, we just divide by its length, v over the length of v. And we call this process, when we divide by the length of the vector, when we find a unit vector in the direction of a vector, we call that normalizing the vector. So if our problem asks us to normalize the vector, what it's asking us to do is find the unit vector in the direction. And all we do is divide by the magnitude. Questions so far? Again, mostly review. Yes.
So for the unit vector, you have like I hat and j hat, and you divide each component by the
Yes.
magnitude?
Mm-hmm. All right. Yeah.
If you have like going between 2 points, for the component one, you like subtract the points to give magnitude.
Yes. Yes. Mm-hmm. All right. So Cole mentioned I hat and j hat. So let's talk about those guys for a second. Those are called our standard unit vectors. So our standard unit vectors are I hat in the plane is the vector 1, 0, and j hat is the vector 0, 1. And we can write, the nice thing about the standard unit vectors is that we can write any vector in the plane can be written as a linear combination of I hat and j hat.
What's the letter they use for one of the third when they go into the third dimension?
Okay.
Okay. I couldn't remember if they did actually go alphabetically or if they went to like some other weird random number. Because that's what calculus does sometimes, let's face it.
So any vector in the plane can be written as a linear combination of I hat and j hat. So if we have, for example, if we have v equals v1, v2, we can say this is v1 I hat plus v2 j hat. And we say that v1 and v2, v1 is the horizontal component of v, and v2 is the vertical component of v. So we can write any vector in the plane as a combination of I hat and j hat just by using its component form like this. Everybody familiar, or everybody feel okay with the standard unit vectors? We're going to be using, and I'll go, like I said, I'll go back and forth just so you'll see the different types, different ways of referring to vectors. I'll use I hat and j hat, and I'll also use bracket notation. I try to use them kind of equally, just so we're all familiar with all the different ways of representing the vectors. All right, so let's relate our vectors back to angles, trigonometry. So that's another nice thing about vectors is we can use vectors in polar coordinates. We can talk about angles. So if we have a unit vector, we have a unit vector u, and I need to get better at writing those little arrows. When I don't do it for a while, they don't come out as nicely. So we have a unit vector u with its initial point at the origin, and its terminal point on a circle And we measure theta, our angle, counterclockwise from the x-axis. We can write that u is the vector cosine theta, sine theta. And this is the same as saying cosine theta I plus sine theta j in the two different representations. And so this gives us a way to represent vectors using polar coordinates. So let me just draw a quick sketch here. So here are our axes. Here's our vector. That's theta. So this component here, if I project this down, that side of the triangle is cosine theta, that side of the triangle is sine theta, and this is my unit vector u here. So this is all we're talking about here. If we have v is not a unit vector, and it also makes this angle theta counterclockwise from the x-axis, we can write v equals the magnitude of v times cosine theta sine theta, the vector cosine theta sine theta. And this is, we can just write it in the other form. This is magnitude of v cosine theta I plus the magnitude of v sine theta j. So this gives us a way to write, if we know the angle, and we know if we know the angle and the magnitude of a vector, we can break it down into its components using this information. Everybody good with this? Let's see, a couple more things I want to mention, and then I will cut you loose on homework. Resultant force. Resultant force, so if we're finding resultant vectors, so I'm just going to say resultant vectors. Resultant vectors just means that we add the components. So if we're finding the resultant, we're just adding the components to find the vector that results from all of these vectors. So all we're doing, if we're talking about a resultant force, a resultant speed, or I'm sorry, a resultant velocity, anything like that, is we're just adding components. And the last thing that I want to mention, often problems that involve resultant vectors have to do with navigation. Math books like to talk about navigation. So, and there's a couple of different ways that we refer to angles when we're talking about navigation and when we're talking about bearing. A bearing.
Pi over 2all.
What's that?
Oh, pi over 2all.
Right.
Everything up.
A bearing is an acute angle from the north-south line.
I thought bearing was just in general measured from the northern pole.
That's a different one.
That's a different
That's a
bearing.
different type of bearing. So
Wow.
so if we're talking about bearing, we're talking about an acute angle from the north-south line. So if the problem gives you the angle as a bearing, it's got, your angle needs to be an acute angle, and it is from the fixed north-south line. So and the direction indicates the line of sight or the direction of travel. So for example, a bearing would be something like, it would give you something like north 30 degrees west. The way that I always read these is, this is 30 degrees west of north. So this bearing, if we were here, and this is my compass, 30 degrees west of north would be this direction here, and that would be 30 degrees. Another example, 59, let's see, south 59 east. This is 59 degrees east of south. So this bearing would be down here like so. So that's what these two angles would refer to. So I always read them kind of backwards. In air navigation, it's a little different. Good question. So in air navigation, the bearing here is usually for surveying and for sea navigation. In air navigation, the bearing is an angle measured clockwise from north.
Clockwise or counterclockwise?
Clockwise.
Okay.
So in air navigation, our angle is measured clockwise from north, with north being 0 degrees. So that's the difference between air navigation and bearing in sea navigation or surveying. So some of your problems we'll talk about bearing, and some we'll talk about airplanes, and they'll give you the angles. Some angles will be like this. In air navigation, your angle would be 330 degrees, and that would tell you you're going 330 degrees, starting with going clockwise with north being 0. All right, questions on our whirlwind review of vectors? I think the best thing to do is just going to be to try some of these problems. If I guess one word of warning, if you're given some vector, if they give you the component form of a vector and you're finding the magnitude and the direction, when you find your angle, you can find your angle, make sure you get your angle in the correct quadrant. So be aware of which direction your vector is pointing. If you're looking for magnitude and direction, make sure your angle gives you the appropriate quadrant for your vector. All right. Homework. This looks like a lot of problems, but a lot of these are extremely quick and easy.
And you did mean 57 and not 67, right? On there, it's on the website, like 55, 67, 59, 61, 62, 65, or 85.
Yes, because what I did was combine two.
So you do want it to be 67?
Yes.
Okay.
Oh, wait. Let me double check. Yeah, I do want it 67.
Alrighty. I wasn't sure because it came up in the middle of the 50s, so I'm like, okay.
Let's see if I can write them in a better order here. 37.
Sean, what is the issue I care about that you can affect me virtually, locally, nationally, and budget? Why do I care about it? What do you mean it's so much? What do you care about? What do you care about? And how it affects me, my generation. Well, not here, maybe.
What's that? Well, some of these are like add these two vectors together.
What's a vector?
So, yeah.
How many is it?
It's